And so if we look at this, so now this is a figure from your mathematics assignment that you're working on. We call this the superposition, okay? And so recall, I was playing with this in our Friday discussion the other day, right? When we look at n is equal to 1, you can see we've got a fair amount of uncertainty. Let me change the color. We have a fair amount of uncertainty in the particle's position with this n equals 1, because we've only put in one momentum state, okay? But now, as we add more of these momentum states, okay, we're building up our superposition, and the uncertainty gets smaller and smaller and smaller, okay? And so I won't continue on drawing the colored arrows, but you can see where this is going, right? As we add more and more of these, we become more and more certain of the position. And I'll just demonstrate for you. I've got that down here. So on this graph, I'm just showing you psi, which means we're going to have positive and negative values, okay? Over here, I've got it as psi squared, so this is the same wave function to describe this idea of the superposition. And if I add two superpositions, or two wave functions in my basis set, then as you can see, I'm getting this constructive and destructive interference that gives me more certainty in the particle's position. And as I keep adding more and more terms in my basis set, right? So here, basically, my basis set, right, is this sum of individual wave functions with, of course, their corresponding normalization constants, which in this case now these normalization constants become weighting factors, right? So in other words, if there was only two of these, it would be 50-50. With three of these, 33%, 33%, and 33%, and so on, okay? And overall now, so this creates my basis set, which is now the sum of all of these wave functions, which I've got right here, okay? So now in one single observation, one eigenvalue corresponding to psi k at that superposition will be found, okay? And what that means is, in the case of n equals 1, right, one single observation might mean that, let's see here, it might mean I find the particle right here. Then I do another observation. Perhaps I find the particle right there. And I continue to keep making observations. And if I make a large number of these observations and I average them all together, I will arrive at my superposition, okay? And so, of course, the more of these wave functions I build in, the more precise my superposition becomes. And so what happens now, the probability of finding that eigenvalue becomes proportional to the normalization constant squared. And now the average of a large number of these observations is given by the expectation value of the operator in question. So what we're doing here now, we're talking about position, okay? So if I wanted to know, you know, a large number of observations, perhaps n is equal to 20, right? What becomes the expectation value of that position? Well, it's where precisely the particle is located, okay? And so once again, right, if I keep adding more wave functions into my basis set, right, my superposition becomes more and more precise. And I can keep cranking this up, right, and you can see just how precise that starts becoming. Okay, oh, it had to calculate, right? It's going to go up to that 1.0 value, right? Okay, so continuing on.